right, everybody. Good morning. Welcome back. This is now week 2, officially week 2 of the summer school. And first off, congratulations to making it through week 1. That was quite the adventure, I think, for all of us. I know you all were working extremely hard, keeping up with all that material and learning really from so many different experts. It was a pretty broad program. I think that one thing I realized is that it may be unrealistic to think that you will be able to learn everything that was said to you. And so I want to emphasize that the expectations of the school are not that you will come out being an expert in every topic that you have heard about. Some of you already have background in these topics. This is intended to supplement the research and the studying that you're already doing, but there are other topics that you've probably never seen before. And that's what the summer school is intended to do, is give you exposure to all of the research activities going on within the Department of Energy and its quantum science centers that will help you understand both what are the priorities in quantum science and technology, but then also how you can engage with Department of Energy in the future. Week 2 will be very similar. There will be additional morning lectures. We'll have the afternoon class activities. And then we are trying to add in a few additional things, including tours of the facilities, both the Spallation Neutron Source, the Center for Nanophase Material Science, and the Oak Ridge Leadership Computing Facility. Now, one thing to bear in mind is that going on these tours will have certain restrictions. For example, you will have to wear closed-toed shoes. So if you're wearing sandals or flip-flops, you may not be allowed on these tours. It kind of depends on the circumstances and what's going on there. So I would recommend on Tuesday and Thursday, making sure that you dress appropriately. In addition, we haven't secured the tours yet, but we are going to try to divide people up into smaller groups in order to go through these. So we'll keep you updated on that, but tomorrow we're hoping we can get some tours of the facilities up here. And then on Thursday, we'll be down at back at the conference center where we were a lot of last week, and we'll do tours of the leadership computing facility. Now, the reason that we get to do these tours is, unfortunately, we've had 2 of our speakers not be able to make it to Oak Ridge, partly due to this cybersecurity update glitch. Yeah. Thank you. Yeah, you guys know what I'm talking about. I'm very glad that none of us are traveling at the moment. So exactly. Blue screens of death. That's right. So we have been blue screened of death. But the silver lining is that we do get to do these tours instead. Okay, let's see, any additional updates? Today is meant to be a little bit cooler than it was last week. A little overcast. There might be some rain in the afternoon and a little bit of rain tomorrow as well, but generally not quite as hot as it was last week. Okay, any questions, comments on anything so far? Are you ready? Oh, yeah. So the question was, who were the speakers that couldn't make it? So on Tuesday, Professor Sabre Kais from Purdue University will not be able to attend. He was going to be talking about quantum simulation for chemistry and other methods. And then on Thursday, Dr. Joe Carlson from Los Alamos National Laboratory was going to be talking about simulations of nuclear physics, and he's not going to be able to attend instead. Also, Dr. An Ling from Pacific Northwest Lab, he is teaching on Wednesday and Thursday. He is having flight trouble. It looks like he may not be here, but he has 2 additional people teaching that class, Sam Stein and Chen-Shu Lee, who are both going to be present to help with that. In the back, Morris.
Some of his talk from previous quantum summer schools were recorded on YouTube, so you can just look it up. Coffee House or something. There's a channel. It'll be on QSC's channel in a couple weeks and months.
Hey, great point, Morris. So just to summarize, Professor Kais actually has several talks online already, including as part of the Quantum Science Center and the Purdue Quantum Coffee House. You can find those on YouTube. Thanks. What was that last part? So you asked on Thursday morning if Professor Carlson would not be presenting online? That's correct. Professor Carlson will not be presenting on Thursday. That's right. The alternative is that we get to have the tours. So, okay. With that, let's jump into our first morning presentation. This is actually a triple feature, I think, if I understand. So we have a team from Fermi National Accelerator Laboratory that is going to talk to you today about some of the work that's going on in quantum control systems, developing something called the Quantum Instrumentation Control Kit, or like what I like to call the kick board. I'm not sure who's actually coming up first. Sara. So first up, we'll have Dr. Sara Sussman to give us the introduction. So let's welcome our speakers.
Oh, okay, that's perfect. No, there's a microphone right here. Yeah. Okay, great. All right. Hello, everybody. You can hear me, right? Awesome. Okay, so hi. Happy Monday, everybody. Hope you guys had a great weekend. So we're gonna start you off this week with hardware. Okay. So who here does hardware? Show of hands. Okay, who here does superconducting qubit hardware? Okay, a few in the back there. Is somebody over there? Great. Awesome. So I'll be starting you off with superconducting qubits because I see that about maybe 80% of you do not do superconducting qubit hardware. Okay, so you did get started off with IBM last week. So Nick Braun and his colleague did talk to you about Qiskit and stuff like that. And we're going to actually be talking about the details of how this is really done in hardware. So we actually have a big team with us today. So Hannah and Paul, can you raise your hand? And Kester? Okay, there's a few in the back, right? Okay, right, of course, they're in the back corner. These guys are going to be our TAs for the afternoon's hardware labs down the hall, okay? So we all do design, fab, measurement of superconducting qubit devices, okay? So this is exciting. All right, so superconducting qubits. So first of all, I mean, this is a really nice figure of the hardware stack. It's from the pre-reading. Did anyone take a look? Great, 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 nice. Okay, well, don't worry, you have all week to ask us questions, look at the pre-reading, look at the figures. We're gonna be showing some of those figures today, but this is a practical guide to superconducting quantum hardware. So there's a lot going on in this guide, and I highly recommend you check it out if you are ever going to use Qiskit, if you are ever going to take a look into any kind of hardware. Okay, so this is the stack for superconducting qubits. It's a kind of scalable, almost CMOS compatible qubit hardware stack, okay? So kind of scalable devices. So Google, this chip that I have right here for you guys is about, 5 by 5 millimeters. And it is not the chip that Google did when they demonstrated the surface code with around 50 qubits. This is something else, probably from the past, with only a couple of qubits. But you can see that it has stacked chips where one has the qubits and one has some of the control hardware on it. Google's not going to show you their actual chip, and in fact, they'll just show you something that looks like a tic-tac-toe board, because chip design is the secret sauce for how do you get the qubits to function. Okay, but I did want to show you this because this is the only picture that I've ever found on the internet of something which is Google Quantum AI. Okay, so this is kind of what a chip might look like. And they demonstrated in 2023 that they could do the distance 5 surface code state preparation of a logical qubit, distance 5, and the qubits have nearest neighbor coupling only because they're etched onto the chip. Okay, so this is what I mean by kind of scalable, like could it scale? Okay, this is a huge question. John Preskill spoke last week and he mentioned that if you had 300 qubits functioning together in a superposition state, or preparing that kind of amount of qubits into a quantum state, it would easily surpass what classical computers could simulate. Okay, so the number we are thinking about might be like a couple hundred for something really, really beyond a shadow of a doubt meaningful for simulation. Okay, so the control, okay, we talked a little about the device. The control is microwave. This is the hardware board that we're going to be using in lab. And we're going to emulate qubit control with that. So these are microwave pulses, and we're going to talk about that. We're going to get into the details of that in today's lecture, okay? Okay, what about the almost CMOS compatible? So could you fab these like you fab a cell phone chip? You know, does it have to be done by graduate students in the clean room, or could you send out for a company to fab it for you on a big wafer like this? So it turns out that in March, there's a paper on the archives. This foundry in Belgium's been working on this for several years if you've been to their March meeting talks, and actually they can do that. They got a yield of 98.5% across a 300 millimeter wafer, and their average T1 time of those qubits there was 75 microseconds, and their best is 150. So that is fully CMOS. So that's what I mean by almost CMOS compatible, is that there's actually several other groups working on this as well, right? So this is coming, okay? Questions so far? Thoughts? Okay. It's interesting, right? Yeah, it's potentially pretty cool. Okay, design. That means that we should focus on design, right? Because maybe the fab can be outsourced to a company. Okay, maybe we should focus more on design. The design cycle, and all these figures are from the pre-reading paper, by the way. The design cycle is complicated. It's a balancing act because you need to, in some way, measure in order to confirm that that you've met your target in terms of your target design parameters for the couplings between the qubits, for their resonant frequencies, for their T1 times, their coherence times. All these things need to be checked. But this validation cycle is costly, so we would really like to be able to simulate the devices and know ahead of time that we are confident we are going to meet our target. Okay? So let's talk about the devices a little. Okay, the transmons. We're talking about transmons today. Although our TAs have experience in a variety of qubits, so you should really ask them what kind of qubit they are using. But we'll talk about transmons for now. And in the labs, we're going to be emulating a transmon. So a transmon qubit is a capacitor. It's like a resonator etched onto the chip, like a regular harmonic oscillator. Except instead of an inductor, it has a nonlinear inductor called a Josephson junction. Who here knows what a Josephson junction is? Okay, great. I won't get too much into the details of that, but I'll mention that the fabrication of a Josephson junction is critical, and I'll show you some more pictures of Josephson junctions. So a Josephson junction in a sentence is a superconductor oxide superconductor sandwich across which quantum tunneling happens and gives you a nonlinear inductance. Okay. So we want the nonlinear inductance so that our resonator actually has unequal energy spacing acting as a qubit where you can isolate any transition as a 0 to 1 transition. You can choose which transition you want as your 0 of your qubit and your 1 of your qubit. Whereas you can't do that for a linear oscillator because all the energy levels are equally spaced. The qubit and the resonator are coupled, oftentimes capacitively, by a small dispersive coupling term. This is called the coupling of the James-Cummings Hamiltonian, where we have a small dispersive shift, small compared to the resonant frequency of the qubit or the resonator. And basically, it allows you to weakly entangle the qubit with the readout resonator, so that when you probe the readout resonator, it allows you to read out the qubit state in a way that is quantum non-demolition, which does not destroy the quantum state. So this is a very weak sort of entanglement, which allows you to kind of probe the qubit state when you probe the resonator. And we're going to show this in lab. Okay. There are both planar and 3D realizations of transmons. The 3D ones, this resonator here is just a literal box, okay? And then you see a little junction inside. Yes? How to make a qubit out of a transmon? Qubit. Yeah, so you can use any of the levels as a qubit or qubit. But the question is it optimized? Like, is the design optimized? You can change the level spacing, okay, to optimize it for different things. But if you have a transmon, you can use it as a qubit or a qubit. It might not be optimal for that, but you can use that because the energy, you can isolate those different energy levels, right? You can use any ones that you want. Yes. Oh, we're gonna talk about that. Quantum non-demolition, we're gonna talk about that. Okay. All right. Okay, more about the design cycle. There's open design questions, even those as important as, for example, could we ever do better than only nearest neighbor coupling? You've learned about error correction last week, and you've learned that it would be nice to be able to have longer couplings and more all-to-all connectivity. You've learned that all-to-all connectivity is really nice. And this kind of architecture cannot support that right now because the qubits cannot, they are etched into a chip, right? They can't move. You can't fly them to each other with optical tweezers. So how could you do better than nearest neighbor coupling? Okay, fabrication. Here's another picture of a Josephson junction. So here's a transmon, the capacitor shunted to ground by a Josephson junction. Here's the Josephson junction. The qubit's electric field is concentrated at the junction. It's right here. It's the overlap made by this thin crust, which you can probably barely see. Okay, so this is the critical dimension of the fabrication. Fabrication is critical for high qubit coherence, for example, T1, the characteristic decay time for the qubit to decay from the 1 state to the 0 state. Okay? Today's records for transmons are around 500 microseconds, particularly one recently demonstrated with aluminum on silicon, which is great because that is CMOS compatible. Okay? Other more interesting materials like tantalum or sapphire are not typically found in any kind of CMOS process. These are for single uncoupled qubits, okay? Take these numbers with a grain of salt because if you try to couple them, the numbers get at least 10 times worse. You can look at the average T1 time for Rigetti or Google quoted in the distance 5 paper, and you'll see it's around 30 microseconds, right? So why should it be so low if it's by the top companies? It's because we don't know how to couple them without reducing their coherence right now. And so design is essential. Okay, so we're mostly going to focus today on controlling the qubits with classical hardware. That's what we can bring to you today. That's what we can provide to you today in our labs. That's what we're experienced at Fermilab. But we do have fab and design spinning up and working. So those pictures are fabbed from Fermilab, those transform pictures. Okay, so the tuning up of superconducting qubits. We need to tune up the entangling gates between pairs of superconducting qubits so that they all work together, but this actually resembles rocket science in terms of the complexity and the different levels of calibration that are required and the amount of automation that's needed to all these different pieces of hardware that function together. The cryogenics, the qubit device, the warm controls. It's basically a systems engineering problem, which goes beyond any one discipline, and it requires active control. Active control is like feedback, feed forward, actively resetting the qubits so that you don't need to wait, that you can do things quickly, okay? We'll talk about that in lab as well. Tune-up, so gate fidelity is that entangling gate fidelity we want to see. With the kickboard, we've achieved basically record high 2-qubit entangling gate fidelity that I know of only one other paper which has achieved the same amount, which is 3/9 gate fidelity, entangling gate fidelity for superconducting qubits. And yeah, this is a recent paper for that. You can ask us about that. But gates only work if your qubit is coherent. Gate fidelity is limited by the ratio of the time it takes to do the gate over the qubit T1 time for any of the qubits that you're entangling. Because you run out when T1 happens. You run out of time, your qubits go away. So that's the real qubit control metric we're considering, not only T1 alone, okay? Okay. Questions? Okay. Yes.
These results are for fluxonium and not transmon?
That's true. That's true. So we did talk about transmons, but these results are for fluxonium qubits. Fluxoniums are the only kind of qubit which has reached, superconducting qubit, which has reached 3/9 gate fidelity, entangling gate fidelity. That's a good point. Actually, we have a fluxonium expert is one of our TAs, Paul. So if you're curious about that, you can ask Paul. Okay, so we have tune-up. This is John Martinez of Google. Who did one of the big experiments, and he mentions that each one of the calibration nodes that you would have to work your way through and automate your way through would essentially be its own PhD thesis. That's how complicated it can get when you're operating 50 qubits. Okay. All right, I'm almost done here, but we're going to talk about in the lab a lot. One thing gate fidelity depends on is readout optimization. How clearly or easily can you probe the readout resonator to see the qubit state? It's an issue of device design, right? Your coupling needs to be right. Your design parameters need to be right, but it's also a control issue because if you don't probe it right, you're not going to see anything, okay? Qubit readout. We're going to talk about all these things in afternoon lab. If you don't happen to be in our labs, you can talk to us about it in detail anytime. But basically, we're going to talk about this throughout the lecture, actually. Sho and Gustav are going to get into this. But basically, the qubit states are separated in phase space between the ground and excited state. And we're going to read out the phase of the resonator, and we're going to distinguish that it's going to be changing. So essentially, we're going to go into all these things and how you really do this kind of qubit readout, but we're going to talk about this throughout the lecture. So please ask questions about it, okay? QND readout, Jenny said on Friday that the one experiment that's demonstrated quantum advantage so far has been LIGO. LIGO people could use a squeeze state of light. It showed that if you added more photons, it just doesn't help because you have more back action. So what does that mean? So basically, last week on the archive, there's a nice paper from Yale showing this again. If you probe the resonator with only one photon, you have good quantum non-demolition measurement, but if you use too many photons, that starts leaking out. That the qubit state kind of leaks away when you're probing it. And so then you have worse QND. So how you do QND is you do successive measurements and you see, did you disturb the qubit when you measured it? That's what QND is asking, okay? And so the record for QND is around 99%. So essentially like 1% of the time you end up disturbing the qubit when you probe it. So you better probe it with only a very few photons, maybe even just one photon. Okay? So that's what QND means. Yes. Yes. Yeah. That's called back action. So your measurement might work, but there's back action happening on the qubit, and it disturbs the state of the qubit. Yeah. Okay, and so the record QND might be around 99%. And readout fidelity, more things from lab, but today's record readout values are exceeding 99%, and there's a nice plot in the supplementary of this paper. Tokyo, Yale, ETH Zurich, Chalmers have all achieved above 99% readout fidelity for superconducting qubits, and again, slightly different implementations. There's lots of noise, which causes readout infidelity. That's this kind of blurriness in the phase space between the qubit states. So this is like a Q-trit for the Q-trit guy in the audience. Okay, that's about all I've got. So we're going to move it on to Sho.
What? Test, test. Is this one on? That's on? Great. Okay, I just want to respond to the question. Super. All right. We good?
Yeah, just speak loudly.
Yep. Yeah. By all means, ask me questions as I go. Okay, so Sara's teed up a lot of interesting ideas, a lot of thoughts about how do we make superconducting qubits? What do we want to do with them? What's the path forward? Now, let's talk about what we actually do with them once we have them. Okay, so let's say Sara makes a qubit. Let's say Hannah makes a qubit. All right, I have a qubit. We have a qubit. What do we do with it? So I have this thing. It's on a chip. It has some Josephson junctions, some resonators, and I want to actually measure it. I want to do some quantum operations. Maybe I want to do computation. Okay, what does that mean? So I have a qubit. I want to control it. That means I want to change its state. It has some quantum state that I want to change. A lot of you probably have seen the block sphere, right? Show of hands. Awesome. Very good. Okay, so there's the block sphere. I am not going to go into this because there's a lot in there. But sure, I have a qubit. let's say we're talking about one of the transitions. So I have a ground state, I have an excited state, right? Ground state at 0, excited state at 1. But as I rotate from the ground state to the excited state, I can take different paths, right? I can rotate around the x-axis, I can rotate around the y-axis. So let's say I do a pi/2 rotation around this axis, I'll put my qubit state there. If I do a pi rotation, I'll make it all the way to the excited state, right? So that's what I'm doing when I control a qubit, is I'm changing the state. And with a superconducting qubit, actually practically hands-on, how do I do that? I'm going to be applying we just for short call it an RF drive. We're going to send some microwave power into the qubit, and that's what's going to do the rotation. That's what's going to change states from 0 to the mixed state, to the in-between state, to the 1, and so on, right? Okay, what else can I do? So I move my qubit around, fine. How do I know where it went? So I want to be able to measure this qubit. It's somewhere on the block sphere. I want to know where it is. So I want to do that measurement that Sara was talking about, where I have this resonator. So I have a qubit, I have a resonator, there's this dispersive coupling, right? I have a resonator that I can actually read out in a classical way, and that gives me information about the qubit. It doesn't tell me where I am on the block sphere, right? You can't do that, but you can do the projective measurement of saying, is my qubit in the ground state or the excited state? So that resonator is something that I can probe with another microwave pulse, an RF readout. I'll send an RF pulse into the resonator, see what comes out, and that tells me which state the qubit is in. And don't bother with the details in this diagram at this point, any of this. We will talk about that in a lot more detail in 10 minutes. Okay, so that's the basics, right? I have a qubit, I need to move it around, and I need to see where it went. Then there's more stuff you would probably want to do. You might want to adjust the qubit's properties. A qubit probably has some operating points, some charge bias, some current bias. You know, the magnetic field that it's in probably changes the energy levels or whatever, and that can be good or bad. You might have an operating point that you want to run your qubit at. You might want to take your qubit out of its normal operating point for a little period of time to do some special operation on it. Let's not get into the details of that because there are a gazillion types of superconducting qubits and they're all different. But that's something you would care about when you're designing electronics, is you will want to be able to control the biases, either long-term or short-term. And one thing you might be doing that for is, okay, I have one qubit, I have one block sphere, right? But if I have multiple qubits, I want to do my 2 qubit gates, I want to interact my 2 qubit states, and how do I do that? Again, there are so many ways to do 2 qubit gates. I am not going to go into that, but I can just broadly say that maybe you do this by applying some drive or some bias shift to one of the qubits. Maybe you hit a coupler that's in between your 2 qubits. In any case, the nuts and bolts, how you do that, there's a lot in common between basic control and measurement of single qubits and how you do 2 qubit gates. It just gets more and more complicated as you scale up. So getting to 50 qubits is hard. Getting to 300 qubits is really hard. Okay, so nuts and bolts time. I have my qubit, right? It's come out of fab. I got to put it somewhere. I should be careful. Qubits are sensitive things, right? Superconducting qubits, right? The AMOs can run at room temperature, great. The superconducting qubits, they need to be superconducting, they need to be cold. And so they're going to go into a dilution refrigerator, right? And well, this does not look very much like a dilution fridge, but schematically, I need to get that thing down to 10 millikelvin. That's pretty cold. I need to still be able to talk to it, right? The real trick is I need to be able to put it down at 10 millikelvin. I need to isolate it from the environment. I need to make sure it doesn't pick up any noise or stray excitation, but I still need to be able to send my control in. I still need to be able to read it out. I just need to make sure it doesn't see anything else other than what I want it to see. That's a hard problem. This is not a cryo-engineering course. This is not a cryo-electronics course. There are a lot of symbols here, but let me just say, you need all of these little blocks. You need to do all of this filtering, all of this attenuation to make sure that your control signal gets in, it hits the qubit, but nothing else does. Hard problems. Your readout needs to get in, your qubit response needs to come out. You need to amplify that enough so that you can see that, single qubit state. Again, you need to do all of this carefully so that even though you have all these amplifiers in here, you're not hitting the qubit with any extra power, anything that would make it decohere. Okay, so that is the thing of PhD theses, right? Making a qubit really work. But let's, please. Yes, no, that's a super good question. So in a fridge, I'm going down to 10 millikelvin. My electronics are at room temperature. So when I have electronics at room temperature, you have thermal noise, right? Everything at 300 Kelvin has thermal noise like black body emission. And that's a real problem when you go down to 10 millikelvin. So I need to sort of cool my signal down just like I cool anything down. And I want to do that in steps. And the way I do that is with these attenuators. I'm going to have an attenuator at 4 Kelvin, which thermalizes my signal to 4 Kelvin, like my thermal noise is down to that level. And then I'll do that probably even more than the 2 stages I have here as I get down to 10 millikelvin. Okay, but let's say that's all been done for you. Let's say we have a good setup that works. How do you really control this qubit? Okay, so Sara showed you energy levels, right? You have a ground state, you have an excited state, and so on. So let's say I want to control a qubit. I want to move it from the ground to the excited state. I want to rotate around that block sphere. There it is again. So I have this energy transition that gives me frequency. So that qubit is going to resonate at that fundamental frequency of that transition. So, all right, quantum is hard. Let's talk about classical mechanics. So your simplest resonant device, right? It's a pendulum. So I have this resonant device. I want to get it to oscillate. And so I'm going to give it a resonant impulse, right? It's going to respond to signals at its frequency. So it wants to swing at a fundamental frequency. I better hit it at that frequency. And then it'll pick up a rotation. All right, obviously, this is very not quantum, but you can get the idea. Now, if I don't hit it at that frequency, right? It's hard, right? You can hit it off resonance. It's not going to behave. It's not going to do what you want it to do. It's only going to listen to pulses at that frequency. Okay, where it gets harder is the phase matters. So I want to hit it on resonance. I want to hit it at the correct phase also, right? If I hit it at the right spacing, but at the wrong time, it doesn't like that either. All right, back to the RF pulses. So here I have a violatory example of some pulses that you might send to a qubit. Let's say your qubit has its intrinsic resonant phase, this orange squiggle, that's just like to guide your eye here. But I have this orange squiggle curve for the qubit, and that's where it wants to get hit. And I'm going to send it a bunch of these pulses. So the qubit's only going to listen to the pulses that are on its resonant frequency, that are in time with its reference. And it cares what the relative phase is. If I'm on phase, so if the phase is exactly aligned, let's say that's my x gate. I'm rotating around the x-axis. If I'm off phase by 90 degrees, my axis rotates by that amount. And so let's say that's a rotation around the y-axis, right? So the phase of my excitation sets the phase of my rotation, the axis of rotation. The amplitude is going to set how quickly the qubit rotates. So more amplitude, I'm going to rotate faster around that axis. Okay, so tricky thing here. If my quantum computation, I'm going to have a bunch of gates. I have some quantum circuit I want to run. I have, let's say, multiple X gates. I want to rotate a qubit at different times, but both times around the same axis. what does that mean in terms of my RF pulses? Let's say this is my X gate, right? I have this pulse, this blue pulse, it's lined up with the orange pulses, it's always hitting at the same time. Which of these other pulses is doing the right thing for it to be the same X gate? Any ideas? So you want to look at the ones that are on resonance, so same frequency, and you want to look for one that's when there's a peak on the orange, when the qubits like lined up, you want to hit it with the blue peak. So I don't know, this guy, no, this guy? Yes, you like that one. Yeah, it's on the two ends, exactly. So on the right frequency and at the same phase. That means your qubit control pulses are also, they're doing the same thing, right? On the other hand, like this guy, let's take a look at this one. This isn't at the right frequency, right? So like I have this one, these peak and trough are aligned, but then here we have peak and peak aligned. That's off resonance. That's I'm hitting it at the wrong times. The qubit's not going to respond. But okay, let's think a little more. Okay, so these are our X gates, let's say. This one, what am I doing here? I have the opposite gain, let's say. I have a peak on the orange, I have a trough on the blue. So that's like same axis, but opposite direction of rotation, right? But you could think of it also as 180 degree out of phase, but positive rotation. Those are just two ways of saying the same thing, right? Okay, so this is your intuition that you're building here, but how do we think of this in sort of a general way? So let's say I want to, so the way, I think what I've been saying so far is basically you want to think of these control pulses in the context of how do they relate to this reference oscillator, right? So please. Mm-hmm. So like these two. Second and fourth. Okay. I mean, what I would say here is this one is on resonance, same frequency, but it's 90 degrees out of phase, right? Like the blue peaks are like pi/2 behind the orange. And so that's going to be, let's say, a Y rotation. And this one, it's just completely off resonance, right? So it's not at the right energy. Probably this doesn't do anything total on the qubit. And so this would give you let's say, a Y rotation, and this gives me, I don't know, it might excite a transition that I didn't mean to excite, or it might just it might give me a rotation in a direction that I didn't expect. So yeah, they won't cancel, they're going to do different weird things. And okay, so let's think again. So each of these pulses, I want to be able to define these in sort of a simple way in relation to this carrier, right? I want to say, okay, this pulse, I don't want to think of it as this complicated 5 wiggles thing. I want to think of it as I took this oscillator and then I multiply it by some simple waveform to make this. So I don't know, any ideas about what that simple envelope might look like? Want to draw it in the air if you have an idea? So out here I have 0, 0, 0, right? I multiply my orange by 0. Out here, I'm multiplying my orange by, like times 4, let's say, right? And it's flat all the way through. So I'm just multiplying by a constant number, and then I'm back to 0. So I would say that envelope is like a square pulse, right? Square pulse, right? Okay. And so you could say the same of this guy because it's the same pulse. And this one where I'm out of phase, where I'm 180 degree out of phase, what's that look like? What do you think? I'm going 0, 0, 0. Yeah, down instead of up. Same square pulse. Okay. Trickier one. What's this one? It's not a positive constant. It's not a negative constant. That's sort of hard to draw in the air unless you can draw in the complex space. Okay, so your finger probably can't do that. All right, let's think of, instead of the orange being this sine wave or a cosine, whatever, think of it as a fully complex sinusoid, right? So e to the I omega t, that's your cosine omega t plus sine omega t, right? If you think of your reference oscillator as this e to the I omega t, then could you make, instead of a cosine, could you make a sine? Yeah, you could multiply by an imaginary number. So this one, I'm taking my orange e I omega t and I'm multiplying it by probably I. So I have a rectangular envelope, but it's imaginary instead of +1 or -1. Okay, we'll come back to this idea of real versus imaginary or complex envelopes. Oh, one more thing. So that's all math. That's how you think about this. How do you actually make these pulses? There's a few ways to make these pulses. And so you're going to really define them in this way, where you have this carrier and you multiply by an envelope. And so there are a few ways to do that, but one way might be you literally make the carrier. I have some signal generator that makes a carrier. So let's say this guy, I'm making a local oscillator. And then I have two other generators that make the envelopes. So I have like the real component of my envelope, my +1 or -1. I have the imaginary component. And then I have this mixer which does math to my signals in an analog way and does the multiplication, right? This is what's called an analog IQ mixer. Not going to go into the RF electronics. I don't understand it, but that's one way. The other way is, let's say you have a FPGA, you have a little chip that can do math. I can say, okay, I can make a e to the I omega t on the computer on an FPGA. It can do math. So I'll generate that string of numbers. I'll generate my envelope as a table of numbers, and I'll multiply it inside the FPGA. It does the math, and then I have a DAC, a digital to analog converter that does that math and turns that into a waveform, and that goes out. Two ways of doing the same thing, whether you do your math in analog electronics or inside an FPGA. Gustav will be talking about how we do that in KIC, where we're doing this way to do math, which is perfect in the digital world and no analog imperfections. Anyway, you're going to get to see, those of you who are in the elective, you'll get to see like making these actual pulses in the lab. All right, so those are some pulses. Yes, please. The orange, oh, that's, in my case, I'm just making something up. I'm just saying, I know my frequency, right? That's a real thing. But where it is, what the phase is, I can just decide, I'm going to say, this is my x-axis. And so then I can say, okay, well, I mean, this is the same phase as that. That's clear. And so I can say, oh, that's my x, and oh, that's my y. I can just say that. One thing that actually brings me to, right, is let's say, how do you do a Z gate? I know I do an X gate like this, I do an X gate like this, that's a Y gate like that. How do I do a rotation around the Z axis? So this is sort of a trick. You don't need to do anything. So I said, this is my X sort of arbitrarily. That was a choice I could make. Phases don't mean anything. I can say, oh, never mind. That's my Y now. I'm going to say that's my Y. I can term myself how I look at the block sphere instead of actually doing anything to the qubit. And then I can say, oh yeah, those are all on the x-axis now, not the y. And that's like I actually rotated the qubit around the z-axis. So this choice is arbitrary, and I can change my mind. Okay, so these pulses, they all look the same, fine. Surely we can do something smarter. So what matters when I do a control pulse? I want to get my gates done quickly, right? Sara mentioned there's this T1 decay. So if I put my qubit at anything other than the ground state, it's going to lose energy to the environment or something. It's going to decohere. It's going to fall down to the ground state with some time constant. And so if I'm really cool and awesome, I have 500 microseconds to do that. Maybe I might have 10 microseconds to do that. It depends. Anyway, you're in a race against the clock. You need to do all of your operations on your qubit before it goes back to the ground state. And so you have a deadline. You want to get your gates done fast. And so here are 3 pulses that you might do. I'm just going to tell you they all have the same phase. They're all X gates. They all have the same integrated amplitude. So like I can apply my gate slowly, right? Long pulse, but low amplitude. I can apply my gate quickly, short pulse, high amplitude. I can do this. What's this? This is like a Gaussian sort of envelope, right? Why am I doing that? Let's think. Okay, but these all have the same integrated amplitude. They're all going to do the same rotation, like a pi/2 rotation, whatever. Why do one over the other? Well, clearly I'd rather do this than that, right? I can get more gates in before my qubit dies. That's nice. Surely, okay, can I just keep going? Can I crank up my amplitude, just go to 11 and get my gates done really, really fast? That would be nice. Is there a limit to how much I can do that? There's always a limit. I mean, if I just did like 1 cycle of this oscillation, what am I even doing anymore? So let's be more precise, mathematical, rigorous. What does it mean to say I can't make my pulses arbitrarily short? So the Fourier transform is what tells you what that limit is. So I have these pulses. Okay, so I've pumped these up to 100 megahertz so I can get good Fourier transforms out of them anyway. By the way, all these frequencies, they're not real. If you do a real qubit, it's probably not going to be running at these like 20 megahertz, 100 megahertz waveforms that I'm drawing here. Superconducting transmons usually like 4 to 8 gigahertz. But if you talk to some of our TAs here, they'll have different qubits, you can ask. Anyway, but so I have these 3 pulses, right? I have this long, low amplitude pulse. I have this short, high amplitude pulse. I have this Gaussian pulse. Let's look at this in the frequency domain. I take a Fourier transform and see what that looks like. I know I'm driving my qubit at 100 megahertz, right? I have power at 100 megahertz, awesome. So it's going to do what it wants, what I want it to do. I'm hitting it on resonance, but what's all of this other crud to the side? So I get my 100 megahertz, but there's also this other stuff out at like 95 and 105. Well, it's down 20 dB, it's down 30 dB, that's pretty good. Maybe I don't worry about it. But then I crank up my amplitude and I shorten my pulse, and what's going on here? So I have these side lobes that are really getting pretty big, like 15 dB down. I have stuff all the way down at like 80 megahertz. I might get worried. I might have a qubit where, you know, I have my 0 to 1 transition, which I want to hit at 100 megahertz, but I might have like a 1 to 2 transition at, I don't know, 110 megahertz. And I'm going to start hitting that. And then my qubit's randomly going to be in the 2 state when I didn't expect that to be. And I'm basically going to have errors on my computation. That's bad. Okay, so basically you don't want your frequency spectrum to be too wide. And this is a trade-off, right? Your Fourier transform theorems will tell you that time and frequency are complementary variables. And so if you go squish in time, you go splat in frequency. And so this is something that happens, that you can't compress your pulses in time arbitrarily. They're going to broaden in frequency. And I mean, this rectangular envelope, it is easy to draw for an example, but it's not ideal, right? The Fourier transform of this rectangle is this ugly Bessel function, and it has all these side lobes, and that's annoying. And maybe you should use this nice little Gaussian, which, why is a Gaussian nice? What is the Fourier transform of a Gaussian? It's a Gaussian. That's useful. So my Fourier transform Gaussian is still a Gaussian, and so it's sort of reasonably compacting the time domain and the frequency domain. I can have a short pulse that also doesn't go crazy in frequency space. And so, I mean, I still can't squish this down arbitrarily short, right? But I can do a lot better. Like now I'm clean all the way to like a few megahertz away. That's nice. Okay, there is more art to this science. There are more complicated pulse shapes for very specific, like I know what my other transitions are and so on. But this is the idea. Okay, so you know how to control a qubit. How do you read it out? I have this dispersive coupling, right? So again, don't pay too much attention to the wiring. The idea is I have a qubit, I have a resonator. So my resonator has some fundamental frequency, right? It will respond at a fundamental frequency in a way that's different from if I just hit it off resonance. And so I can measure that. The resonant frequency of that resonator is going to depend on whether that qubit is in its 0 state or its 1 state. And so I can use that. So just high level conceptually, I'm going to hit my resonator with a probe pulse when I want to measure my qubit. I'll hit the resonator, I'll see what comes back. So in this picture, I'll send my pulse like this, it'll hit my resonator, it'll reflect, it'll come out, and here I'll get some digitized signal out of that. And I'll measure that, and I'll look at it and decide, oh, the resonator is at the higher frequency, or the resonator is at the lower frequency. And that tells me, oh, I'm in 0 state or in the 1 state. Okay, what's that really mean? Again, this is something we'll see in the labs. But how does this work? All right, resonators. What do resonators look like? And how do I know what frequency my resonator is at? So what can a resonator do to a pulse? What can anything do to a pulse? I have a linear device. What's it going to do? Oh, linear devices, all they can do is change the amplitude or change the phase. Okay, so let's look at an example resonator and look at it as a function of frequency. I change the frequency. I'm going to change the transmitted power. Sorry, no labels, but I'm going to change the power. So, you know, when I hit my resonant frequency, at least for this resonator, I have a minimum in the power I see. So I go down by 20 dB, my signal goes down by an order of magnitude. Let's also look at the phase. My phase on the red curve, it rotates by, like 0.3 cycles. So a third of the way around the circle, 1 radian, whatever. Okay, so basically I send my probe pulse in. When it comes out, it's going to be multiplied by some overall gain factor, and it's going to be rotated by some angle. Again, we can think of this as a complex number, like there's this coefficient that I'm multiplying my probe pulse by, and that's what I'm going to be looking at is this, the jargon is S21 for I sent a pulse in on port 1 and I read it out on port 2. Anyway, I'm measuring this complex number, and that's what I'll base my decision on. So when I have my qubit, basically this resonator is going to shift to the left or right. So back to this picture, right? Right, so like if my qubit is in 0 state, the resonator looks like this. My qubit is in 1 state, my resonator looks like that. And so if I want to know what state my qubit is in, I need to be able to distinguish resonator is to the left of me, let's say, and resonator is to the right of me at higher frequency or lower frequency. And I mean, there are different ways to do that, right? That's not the only way. You could park yourself at here at the ground state frequency and see if the resonator moves away from you. Different ways, but basically you're going to look at the magnitude and the phase to see whether the resonator frequency has moved. So let's look at this. Let's say I actually do this. I play a probe pulse. So I have this blue probe pulse, wiggle, wiggle, wiggle. I play this blue probe pulse to hit the resonator, and what comes out is this orange thing. And let's see how that looks in these cases where either the resonant, so I'm always listening, I'm always playing my probe at 20 megahertz, but my resonator might be at 20.5, 20.0, or 19.5. So higher, lower, or the same. And so like that's like I'm reading out on resonance or just to the left or just to the right, okay? So what, I don't know, qualitatively, how does the orange pulse look here? So my blue pulse was this nice rectangular thing at amplitude 1. What do you notice about the amplitudes of these 3 orange returns? Top is like big, like you lose some power, but not a lot, right? You lose half your power, say. Bottom is like the same, right? The middle one, you really lost a lot of power, right? And that makes sense here, right? If I'm here or here, I'm losing, oh yeah, 6 dB, that's half amplitude, sure. If I'm losing 18 dB or whatever, I am really killing my return power. Okay. What do you notice about the phase? How does the phase of the orange relate to the blue? My eyes can't make that out. I should do some processing. I should do some math to tell me what the relative phase of the blue and the orange are. Let's go back to that idea of complex envelopes. So we talked about how you can make control pulses by multiplying the carrier by a complex envelope, right? Let's run that idea backwards and think about, okay, I had this orange pulse. Let's think about how I would multiply my carrier to get that. And so I can take this wiggly orange thing, which, you know, it has some shape and it has some wiggliness. I don't care about the wiggliness. I just care about what is the shape. And so I want to get from this a complex envelope that doesn't oscillate, that just tells me what's the magnitude and the phase of the signal coming back. So basically, I am taking the orange, I'm dividing by the e to the I omega t and getting back a rectangular-ish envelope, not very rectangular. And so, okay, we do this. The convention is that this gives you like a time series of complex numbers, right? It gives you a waveform that's complex. Complex numbers are hard to plot. And so we say, okay, there's a real component and there's an imaginary component. And so I say like there's an in-phase term, this magenta, and there's a quadrature term, this blue. And basically all that means is if I take a cosine and multiply it by the in-phase, I take a sine that I multiply by the quadrature, I'll get my orange. So just, there's a convention, right? This is just like how people like to plot things is I take my complex envelope and I say, this is my I component in phase, Q component, quadrature. This is just how people like to do this. Engineers have ways they like to plot things. Anyway, so now you can see, like you don't see the wiggles, you can just see what are the relative amplitudes of the in-phase and quadrature terms. So basically you can see that like, okay, sure, I could already see that the magnitude was different between the 3 cases, like these keep more magnitude than this one. I can also see that the phase response changes. Like this one, right? My in-phase term is positive, my in-phase term is negative, my quadrature term stays positive. So that's like in phase, negative, that's that way left on the real axis. Quadrature is positive, that's like up there on the imaginary axis. That's like in the IQ plane, the complex plane, that's like this point maybe. I say because I made that plot. Okay, and I can do that sort of game for all 3 of these, right? I can reduce this data further to a single data point by saying, I'm going to average over some window, some time window, where I take all those IQ points, I sum them together, and I get one data point. I can plot it on the IQ plane and say, okay, as I change the resonator frequency, I trace out these points. So I don't know, that one is this guy, and then this guy, and this guy. If I do a frequency sweep, I could maybe see like this circle. Why is that a circle? Oh, that's resonator theory. We'll talk about it in lab. But okay, so that's sort of the idea. You do this readout, you get this orange thing, you reduce it to a simple IQ number, 1 point in the IQ plane. That's nice. There's some art to like, oh, what's the right integration window? Maybe that's something to chew on, and we'll really talk about it in lab. Okay, but I do my readout. I get a point in the IQ plane. I do many readouts. I do many experiments. I run my circuit 1,000 times. I get 1,000 points in IQ space. I get all these points. I can plot them in the IQ space, and I get sort of these blobs. I can make a histogram. I can get all these points, and I can be like, oh yeah, these are my my excited states. So all of these points are sort of clustered around here. That's my qubit is in the excited state, and my resonator frequency is there. These are my ground state where my resonator frequency is there. And so I can do this separation where like I can read out my qubit state, project it onto the resonator, put it on the IQ plane and say, okay, now I can like project this onto the x-axis and say, oh yeah, this peak is the ground state events. These are my excited state events. And I can say, okay, so like I can't, like if I have an event that's here, I don't really know which it is. So that's fidelity, right? This idea that I can't perfectly identify all of my events. Like maybe 93% of the time, I will be able to, like the point will end up clearly on one side of my threshold, the correct side of my threshold. And if I want better fidelity, if I want to better isolate my ground and excited states, I want to, I don't know, move those blobs further apart. So make my signal bigger, or I want to make those blobs smaller to compress the noise, right? This is a signal to noise sort of thing. The better my signal is relative to my noise, the better my readout is, the better my fidelity is. And I can do that by reading out for longer. I can do that by reading out at more power. Can I really? Yes, please. Oh no, probably not. Yeah, like could you repeat it? Could you get all of these measurements from a single shot, like before your qubit decays? No. Like, yeah, like maybe each measurement takes a microsecond and your qubit lives for 50 microseconds. Yeah, maybe you get 50 shots in there. And anyway, your measurement's not perfectly QND, right? Like when you do this measurement, you have some action on the qubit and you might disturb its state. So no, this is going to be like, I have my circuit. I'm going to run the circuit from state preparation through to the end 1,000 times. And these are my results. So yeah, if I want to get better fidelity, I use more power, or I read out for longer. I can't keep using more power, right? Sara told us about this effect where, yeah, you put too many photons in the cavity, you destroy your QND-ness. You basically are no longer in the dispersive regime. And so like, if you exceed some critical photon number, your readout is no good anymore. So you can't put too much power in, and so maybe you just want to reduce your noise, right? You want to be in this situation, nice clean blobs, not this, like my amplifier spreading my data around like that. And so you want good amplification. There are parametric amplifiers that are really good that like give you the theoretically ideal quantum limited noise. And so a lot of people do a lot of work on making those really good. Okay, but like this general idea, making your readout fidelity better by cleaning up your signal to noise, like picking the right readout window and stuff like that. Yeah, we'll talk about it in the lab. Okay, I am way over my time for my segment, and it's Gustav's turn.
All right. So what we need to have in mind is that if you are developing a quantum computer, you have three things to do: state preparation, state evolution, and readout. And this is what Sho and Sara have been talking about. And potentially, you have decoherence of the qubit, and decoherence produce errors. So in your quantum computer, you need to be very careful, and that's why controlling a quantum computer is hard, okay? And of course, not only there is decoherence, but there is also noise added to the readout and to the preparation of a qubit. So single readout, like showed, is not going to be accurate, but we rely on something that is called the Chernoff bound, in the sense that if we prepare the system again and again and again in the same way, very carefully, and that requires accurate control, and then you average all those results, the advantage over the 50-50 chance in the experiment will converge to a number. So some people will say, oh, okay, but if I have a qubit and the qubit is an analog qubit and the Bloch sphere, I can put the qubit in any place. So why I don't have infinite information in a single qubit? Why do I need more than one qubit? Well, knowing exactly with infinite precision or accuracy the value of that vector in that Bloch sphere will require infinite trials and also infinite storage, okay? So we can't do that. And I'm gonna skip this, but the idea that the qubit or a system of qubits is quantum mechanics and evolves with a Hamiltonian, and we are actually using classical electronics or optics, depending on the qubit, to control it, is an absolutely amazing idea, right? You are messing around with quantum information using classical equipment, okay? And like Sho said, you use the Fourier transform. So the time and frequency domain are very important, okay? And you need to craft your control looking at both. I think I can skip pretty much this slide, but keep in mind that there are many technologies for qubits. So if you are building a quantum control system, either you are building very specific control for one particular type of qubits, or you aim at a more general system. That's what we have been doing, trying to build a quantum system control that can be used for many types of qubits. It has to scale up. It has to be open to everybody, right? Otherwise, we can only afford it at big companies like IBM, Google, or Amazon. And we open these as an open control system for everybody. And it has to be cost effective, right? Only in the last 5 years, people have thought about controls as an integrated part of a quantum computer or a quantum lab. Before that, they used a bunch of off-the-shelf equipment, and that was very expensive. And of course, there will be big companies that are going for the big chips, like the Sycamore chip at Google, the Osprey chip, 433 qubits at IBM, but that requires a refrigerator cabled up like that, and that probably costs $10 million. But in the labs, we do things differently, okay? So we try to, instead of going for the massive amount of qubits, we go for improving qubits. And there is a lot of work. I don't think quantum computers will be available without all the knowledge, all the know-how that will be developed at the universities and small labs and small companies, okay? So a factor of 10 improvement in fundamental qubit parameters is equivalent to a factor of 4 or 5 in the number of physical qubits that you need to realize a logical qubit. Okay, and that's crucial. So if we can make the T1s and the T2s and all the parameters that they've been talking about a factor of 10 better, that is a big payoff. Okay, most applications of QIC are focused on those problems. Okay, qubit characterization, fabrication, testing, and so forth. Okay, so what is QIC? QIC is an open source, off-the-shelf piece of equipment that relies a lot of the custom firmware and the custom software that the QIC team has developed. You can go to the GitHub, check it out. We have a companion board for optimizing RF frequencies that is not yet available commercially, but it will be in a short term. And there are 4 different platforms that we support. The one in the figure is a smaller one that we're going to be using in the lab here. It's called the 4x2, but there are other ones that we call the CCU 111, 216, and the 208. The 111 is a little bit older, so we don't recommend people to buy that one anymore. But since we've been talking about superconducting qubits here, we have focused development a lot on superconducting qubits. But later, we also took on the job of supporting other qubits like AMOs, NV centers, and also quantum detectors in quantum networks. Okay, so we have IP in the firmware and in the software to support that. Detectors, for example, MKITs, SNSPDs, which are nanowires, quantum capacitor detectors, even a broadband antenna. Okay, so the old type of control is replaced by a simple box, and some people like it. So you have quotes for people like David Schuster at Stanford, who says that QIC has actually allowed his lab to think differently about the experiment that they can reach with control. Okay, that's very cool for us. Well, show this. So I don't need to explain why we use a lot of Gaussian pulses, and also show this. But the important point here is that there are some reasons. Sara explained that. For example, the critical number of photons that you can put in a resonator that never allows fidelity to be 100%. Okay, but there are also reasons why noise in the electronics reduce fidelity. So with better control, we can approach better fidelity numbers. Okay, it's not only qubit design, but it's also control design. Okay, this is the, let's say, the top of the line kind of hardware. We call it the board here is called the CCU 216. It goes up to 10 gigahertz, 16 channels, which is quite a bit for controls. And all the, like Shaw mentioned, all the up conversion of signals and the down conversion of signals in the RF domain is done digitally, which avoids using analog mixers. Analog mixers drift, have calibration problems. So you can have a very stable run of your experiments for an entire day or more without drifting. That's very important. And the front board is the custom design at Fermilab RF board that we have a couple working, is working very nicely, but we hope we can make a production for customers. Okay, for qubit device using the system at Fermilab. okay? More of the same. And what is under the hood? Okay, so we have a piece of firmware. And yeah, you can do this. I mean, conceptually, you could say, oh, I can use a waveform generator to do this thing. But we have 16 of these blocks inside a single FPGA that is about this big, okay? So that's much more efficient. And we can have, yeah, we can have frequency and phase relationships and timings, very fast timings, operating on that FPGA. So this is great. A set of signal generators, everything in the digital domain, that then they are converted to analog signals out of the DAC. And then for the readout, we sample signals with the ADC, and then we do the pulse integration or more complicated filtering that you can even think about using AI for recognizing pulses or optimal control or whatever. And there is a small processor built in logic, and that processor can actually feedback states. So if you have a conditional quantum programming in which your program is conditioned by the state that you read out, you can jump and continue doing that. Okay, on top of the firmware, we have software, and the software is based on a tool created by Xilinx University called PINQ or PYNQ. It's a very nice tool because it sits on top of the Linux, and it manages very easily the logic on PINQ, on Python in a browser. So you can program your computer, your quantum computer program. You can program that. You can access the logic blocks through the PINQ system. Okay, and a little bit more detail on the FPGA. You have the programming logic here, and you have the software blocks, the processor running PINQ and Python. So this firmware is located in this part, and the software is located in the other part. Okay, so what can you do with QIC? You can directly interface to a single or multiple qubits. We can also frequency multiplex qubits. So you save RF lines by frequency multiplexing the readout of qubits. Hopefully, we can multiplex controls in the future, but not yet. We can sync up signals across the board. We can sync up to with a PLL to 80 femtoseconds. Waveforms are all parametric. You can do characterizations of qubits to the push of a single button. So you can read this later. Okay, so this is a plot from our first paper. So you can see that you can do resonator characterization. You can do qubit characterization. You can do Rabi and Ramsey fringes oscillations experiments to measure T1, fidelity, and so forth. Okay, this is very basic, but you do it all the time. This for a multi-qubit system, you can demonstrate how well your entanglement is and the fidelity of your gate by using our control system as well. This is a more complicated experiment. This is, I think, a 4-qubit multiplex readout experiment. The plot here shows how these qubits are read out in different channels in the frequency domain. And then for detectors, that's very important for the people who are working in quantum sensing, like dark matter experiments, axion experiments, and so forth. We have a different conceptual diagram for the firmware, but this allows, by using what is called polyphase filter banks, to analyze. Let's say in this ADC, you read 1,000 channels. And like in a telecom industry, you you have 1,000 messages or phone connections going on a broadband channel that then they get split into 1,000 different channels, and everybody listens to the private conversation. And this is what's happening with each pixel in a detector that is farther upstream. Those detectors need to be typically read out in the same way qubits are read out, but with continuous signals, okay? So you excite the resonator at the resonance frequency, and when a photon hits the detector or something like that, the resonator will move in frequency, and you will measure something. And you can do the same IQ loops, and you can look at the amplitude and the phases in the same way, but with continuum waveforms. We have done other cool experiments in sensing, like, for example, 500,000 point fast Fourier transform for a broadband antenna axion experiment. I'm not going to go in detail because I'm running out of time. And for quantum networks, we use detectors called nanowires or SNSPDs. These detectors have the peculiarity that have a picosecond resolution, a few picosecond resolution. So this is the resolution that we have obtained on our control system, less than 2 picoseconds. The detectors themselves are not there yet, so our control board can measure very accurately 10 or 20 picosecond resolution of the detector. And with that, we can speed up the generation and the measurement of the entangled photons in a quantum network system. Okay, I think that's all I'm going to say, and thank you.
Folks, so we're getting ready for our break. I'm sure that the entire team will be happy to take a few questions. If there's any emergency questions you need to ask right now before we take a break, raise your hand real quick. Got one over there. Shout it out.
So, can you go back to the slide where you showed what detectors can do? I saw a very particular keyword for QCD, and I'm very curious about what part of QCD is being measured using these detectors.
Quantum capacitor detectors?
Aha, I thought it is quantum chromodynamics, sorry. Thank you for clarifying that.
QCD is quantum capacitor detector. Actually, we are putting a proposal together, an experiment that is going to be called Ladera, and that is an array of quantum capacitor detectors designed by a person at Caltech, and is an astrophysical detector for axions. Okay. Measure the deviations of the cosmological constant from being a constant.